Chapter 9. Neural Networks in Practice. 9.1 Case Studies, Successful Deployments of Neural Networks. Neural networks, a subset of machine learning algorithms inspired by the workings of the human brain, have been successfully deployed across various industries, transforming traditional business models and creating new market opportunities. This section will explore notable case studies where neural networks have been effectively applied, demonstrating their practical impact on real-world problems. One prominent example is in the field of healthcare, where neural networks are used to analyze medical images. A neural network, trained with thousands of labeled images, can learn to identify patterns indicative of diseases such as cancer. In particular, deep learning, a type of neural network with multiple layers that can capture hierarchical features, has shown remarkable success in detecting malignant tumors with a level of accuracy comparable to that of expert radiologists. The advances in neural networks for image recognition not only increase diagnostic accuracy, but also significantly reduce diagnostic lead times, facilitating earlier and more effective treatment interventions. In finance, neural networks have revolutionized the way companies assess creditworthiness and manage financial risks. By analyzing vast arrays of consumer data, including transaction histories and social media activity, neural networks can predict individual credit scores with high precision. Furthermore, they are employed in algorithmic trading, where they process market data to identify investment opportunities and execute trades at speeds unattainable by humans. The deployment of neural networks in algorithmic trading has made markets more efficient while also creating new challenges in terms of regulatory oversight and market stability. Another sector that has been fundamentally altered by neural networks is transportation. Autonomous vehicles, guided by neural networks, are becoming increasingly commonplace. These neural networks process input from various sensors, including lidar, radar, and cameras, to enable the vehicle to navigate complex environments. They must make split-second decisions about speed, trajectory, and obstacle avoidance, all while continually learning from new data to improve performance. The success of neural network-based autonomous driving systems illustrates the potential for neural networks to manage tasks with a high degree of complexity and uncertainty. Retail companies have also harnessed neural networks to improve customer experience and optimize supply chain management. Through personalized recommendation systems, neural networks analyze individual customer data, including past purchases and browsing behavior, to suggest products that align with their preferences. These systems help increase customer engagement and sales by providing personalized shopping experiences. Additionally, neural networks are employed in inventory forecasting, whereby they analyze sales data, seasonal trends, and other factors to predict stock requirements, reducing waste and stockouts. In the realm of natural language processing, NLP, neural networks have brought about a significant leap in machines' ability to understand and generate human language. Language translation services, such as those offered by Google Translate, utilize neural networks to provide translations that are often indistinguishable from human translations. These services have improved cross-cultural communication and have been vital in breaking down language barriers across the globe. Moreover, virtual assistants powered by neural networks can understand spoken commands and respond appropriately, facilitating smoother human-computer interaction. In agriculture, neural network applications are optimizing crop yield and resource management. By analyzing data from satellite images, soil sensors, and weather reports, neural networks can advise farmers on planting schedules, irrigation, and fertilizer usage. This data-driven approach assists in maximizing yields and minimizing environmental impact, contributing to more sustainable agricultural practices. Precision agriculture enabled by neural networks is a powerful tool in addressing the increasing food demands of the global population. The field of energy has also seen the benefits of neural networks, especially in predictive maintenance of industrial equipment. Neural networks can monitor and analyze data from sensors on machinery to predict failures before they occur. By preemptively identifying issues that could lead to downtime, neural networks facilitate maintenance operations and can substantially reduce operational costs. Additionally, in the realm of renewable energy, neural networks are used to forecast energy production from sources like wind and solar power, which is inherently variable, thereby enhancing the reliability of power supply from these renewable sources. Consumer electronics is another area where neural networks have made a considerable impact, particularly in smartphones and cameras, where they improve image and speech recognition. For example, neural networks are integral to the facial recognition technology used for device security and user authentication. The deep learning models deployed within these devices are trained on a diverse array of facial data, enabling them to recognize a user accurately under various lighting and orientation conditions. Furthermore, these networks contribute to enhancing photograph quality by adjusting settings such as exposure, focus, and color balance in real time. In entertainment, neural networks have been pivotal in video game development and special effects in movies. Games now feature non-player characters, NPCs, that learn and adapt to the player's behavior, creating a more engaging and challenging experience. Movie studios use neural networks to generate realistic visual effects. For instance, they can be trained to replicate the nuances of human facial expressions, leading to more lifelike animations. The cutting-edge technology behind CGI has opened up new creative possibilities, allowing for the creation of scenes and characters that were previously infeasible. Finally, the integration of neural networks in cybersecurity demonstrates their capacity to protect against complex and evolving digital threats. Neural networks can detect anomalies in network traffic that indicate potential cyberattacks, such as malware or unauthorized access attempts. Due to their learning capabilities, neural networks become increasingly adept at identifying new types of cyber threats, improving the security posture of organizations. The application of neural networks in cybersecurity not only helps in proactive threat detection, but also in automating the response to security incidents, therefore limiting damage and expediting recovery efforts. 9.2 Building end-to-end neural network projects. Building an end-to-end neural network project demands meticulous planning, interdisciplinary knowledge, and practical skills in both software engineering and machine learning. The term end-to-end refers to a project where a neural network is responsible for all aspects of the task, from input handling to the final decision or prediction, without human intervention within its operation. The following section outlines the typical stages and considerations involved in creating an end-to-end neural network project, demonstrating the process from conceptualization to deployment. Before coding commences, defining the problem is the first critical step. This involves identifying what you want your neural network to solve, which influences the architecture you'll design, the data you'll collect, and the evaluation metrics you'll use to measure success. Clear problem definition helps avoid scope creep and ensures that your solution aligns with project objectives. For instance, discerning whether the task is a classification, regression, or sequence generation problem will dictate the neural network's structure and the nature of the output layer. Data collection is the next pivotal phase. Neural networks require substantial amounts of data to perform well. This data should be as representative of the problem space as possible, to ensure the network learns the underlying patterns rather than memorizing specific examples. In some cases, data augmentation techniques can expand a limited dataset, increasing diversity and volume. Data quality greatly impacts model performance, making the processes of cleaning, normalizing, and pre-processing data crucial steps that should not be overlooked. The architecture of the neural network is designed based on the problem type and data characteristics. Layer types such as dense, convolutional, recurrent, or transformer layers can be chosen according to the input data's nature and the complexity required by the task. In addition, considerations regarding the depth and width of the neural network, activation functions, and regularization techniques must be addressed. Selecting the right architecture is an iterative process that may require experimentation and modification as the project evolves. Once the network architecture is defined, selecting an appropriate loss function and optimizer is essential for training. The loss function quantifies the difference between the network's predictions and the actual data, guiding the network towards better performance. The optimizer algorithm influences how the network updates its weights in response to the loss function. Choices of loss function and optimizer have significant effects on the efficiency and outcome of the training process. It is vital to understand the implications of different options and select the one appropriate for your specific problem. Training the model involves feeding the pre-processed data through the network and using backpropagation to adjust the weights. This step requires considerable computational resources, particularly for large complex datasets or deep neural networks. To manage computational demands, training may be performed in batches, and techniques like parallel computation or distributed training across multiple GPUs may be employed. Monitoring metrics such as loss and accuracy during training helps assess model performance and determine when a model has reached its peak or is overfitting. Validation of the model on a separate dataset is a necessary step to ensure that the model generalizes well to unseen data. This step often reveals if the model has learned to generalize or has merely memorized the training data. Tuning hyperparameters, such as learning rate, batch size, and network dimensions, is an iterative process that usually follows model validation. This process requires a methodical approach, often using strategies such as grid search, random search, or more sophisticated methods like Bayesian optimization. After model validation, further refinement through techniques like transfer learning, ensemble learning, or fine-tuning of the layers might improve performance. Transfer learning leverages pre-trained models on large datasets to benefit smaller projects with limited training data. Ensemble methods combine several models to reduce variance and improve predictions. Both strategies require careful implementation to prevent complications, such as exploding computational requirements or overfitting. Integration of the trained neural network into a production environment involves additional steps. Ensuring that the model performs reliably in real-world conditions requires thorough testing under various scenarios. Additionally, designing a pipeline for the continuous delivery of input data, model execution, and handling of outputs is necessary for an integration that's seamless to the end user. Scalability and efficiency are key considerations for production, prompting the use of optimized frameworks and hardware acceleration wherever possible. Monitoring and maintaining the deployed model are constant requirements. Over time, models tend to drift as real-world data changes or evolves, leading to decreased accuracy and the need for retraining or updates. Setting up a system for monitoring model performance in production, detecting drift, and automating retraining with new data is crucial for maintaining the relevance and accuracy of the neural network. Documentation and knowledge transfer are often understated yet significant aspects of creating an end-to-end neural network project. Comprehensive documentation that includes details of the problem definition, data pre-processing steps, model architecture, training procedures, and deployment methodologies facilitates maintenance and future enhancements. Proper documentation ensures that knowledge is preserved and transferable, enabling teams to build upon the project's achievements for subsequent initiatives or reference in problem solving. Each of these steps addresses important aspects of assembling a neural network project that not only performs well, but also stands up to the rigors of real-world applications. As the field of neural networks evolves, professionals must keep abreast of emerging practices and technologies while applying these foundational principles to deliver effective, efficient, and reliable AI systems. These guidelines provide the milestone checkpoints necessary to structure a project's development and to ensure its success from idea conception all the way through to a fully operationalized neural network system. 9.3 Data collection and pre-processing for neural networks. Data collection is a crucial first step in creating neural network models. The quality and quantity of data directly influence the performance of the model. When collecting data, it's essential to capture a comprehensive and diverse dataset that reflects the problem domain accurately. Data can be sourced from several areas, including public datasets, internal logs, crowdsourced information, or generated synthetically. Regardless of the source, the key consideration should be on ensuring that the data is representative of the scenarios where the neural network will be deployed. For instance, in an image recognition task, if the model needs to recognize objects in various light conditions, the training dataset should include images with those varying conditions to prepare the model effectively. Once data has been collected, it must be examined for quality. Data quality checks involve identifying missing values, outliers, and errors that may impact the neural network's learning process. Data often requires cleaning, where missing values are handled, either by removing the affected records, imputing values using statistical methods, or estimating them with more sophisticated machine learning methods. Outliers need attention since they can skew the training process. However, care must be taken to distinguish between noise and valuable but rare data points. Erroneous data, which can be the result of collection errors or data entry mistakes, should be corrected or removed to prevent the propagation of inaccurate information through the model. Pre-processing data is a foundational step that transforms raw data into a format that neural networks can work with efficiently. Pre-processing can include normalization, where feature values are scaled to a common range, such as between 0 and 1, or standardization, which scales data to have a mean of 0 and a standard deviation of 1. This step helps in accelerating the convergence of neural networks during training and prevents certain features from dominating purely because of their scale. Additionally, feature encoding is critical when dealing with categorical data. Techniques like one-hot encoding or embedding layers in neural networks allow the model to treat categorical data appropriately. Feature selection and feature engineering are processes that can dramatically impact the performance of a neural network. Feature selection involves identifying the most important features that contribute to the prediction outcome and removing irrelevant or redundant data. This can not only improve model accuracy, but also reduce training time and model complexity. Feature engineering, on the other hand, is the art of creating new features from the existing ones. It requires domain knowledge and creativity to design features that enrich the model's input with information that can enhance its predictive power. For instance, in time series data, engineered features might include rolling averages or time-based decay factors that capture temporal trends relevant to the prediction task. Balancing the dataset is another crucial pre-processing step, especially in scenarios where some classes are underrepresented. Imbalanced datasets can bias the neural network towards the majority class, leading to poor generalization. Techniques such as oversampling the minority class, undersampling the majority class, or generating synthetic samples using algorithms like SMOT, synthetic minority oversampling technique, can help achieve balance and thus more robust neural network performances. Partitioning the dataset into training, validation, and test sets is a best practice for evaluating the neural network's generalization capability. The training set is used to train the model, the validation set is for tuning hyperparameters, and the test set is reserved for a final assessment of the model's performance. Cross-validation techniques, such as k-fold cross-validation, can be employed for more reliable evaluation, whereby the dataset is split into k smaller sets and the model is trained and validated k times. Each time, a different set is used for validation, and the remaining k1 sets are used for training, yielding a comprehensive performance overview. Data augmentation can significantly enhance the dataset size and variability, which is particularly useful in domains like image and speech recognition. Augmentation artificially increases the diversity of the dataset by applying transformations such as rotation, scaling, cropping, or noise addition to data samples. These transformations help the neural network to learn more generalized features and are less likely to overfit on the training data. However, it is important that the augmentations are relevant to the problem context and do not introduce misleading information that could harm the model's ability to generalize. Dimensionality reduction techniques can be employed to reduce the complexity of the data. High-dimensional datasets can be problematic, as they may contain a lot of redundant or irrelevant information, leading to overfitting and increased computational costs. Techniques such as principal component analysis (PCA) or autoencoders can distill the data into a lower dimensional space while retaining most of the relevant information. In the context of neural networks, autoencoders can be particularly powerful as they are designed to capture nonlinear relationships in the data. Temporal and sequential data come with their own set of pre-processing challenges. Time series data often requires detrending, deseasonalizing, or normalization to ensure consistency and relevance in temporal features. When dealing with sequences, it is crucial to maintain the right order of data points and possibly pad or truncate sequences to have uniform lengths when feeding them into neural networks such as long short-term memory, LSTM, or gated recurrent units, GRU. Lastly, data integrity and security during the collection and pre-processing stages must be considered, particularly if the data is sensitive or personal. Ensuring compliance with data protection regulations, such as GDPR, and maintaining high standards for data encryption and anonymization can protect against data breaches and unauthorized access. It is vital to keep an audit trail of data handling processes to maintain transparency and accountability. As we have detailed, data collection and pre-processing are vital steps in the journey towards developing a functional and efficient neural network. Starting with careful collection, moving through diligent cleaning and pre-processing, and ending with the application of domain-specific techniques, this stage of neural network development sets the foundation for what is to come in subsequent stages of model building, training, and deployment. Practice in this area involves a combination of meticulous data science, an understanding of the mathematical underpinnings of neural networks, and a commitment to ethical standards in data handling. With the right approach to data collection and pre-processing, one can lay the groundwork for neural networks that are powerful, accurate, and applicable across a wide range of practical tasks. 9.4 Model Evaluation and Validation Techniques. In the domain of neural networks, model evaluation and validation are critical processes that ensure the reliability and generalizability of a model's predictions. Model evaluation entails using various metrics to measure the performance of a neural network, while validation involves methods to ensure that the model performs well on unseen data, which is fundamental to achieving robustness in machine learning tasks. One of the cornerstone approaches to validation is the concept of a training and test dataset split. Typically, the available data is divided into two parts, the training set and the test set. The training set is used by the neural network to learn from the data by adjusting its weights, while the test set is used to evaluate performance. It acts as a proxy for new, unseen data. The goal here is to ensure that the performance of the neural network on the test set is a good indicator of how it would perform in a real-world scenario on unencountered data. Cross-validation is a more advanced technique used to validate a model's effectiveness. The most common form of cross-validation is k-fold cross-validation, where the dataset is randomly partitioned into k equally sized subsets. Of the k subsets, a single subset is retained as the validation data for testing the model, and the remaining k1 subsets are used as training data. This process is repeated k times, with each of the k subsets used exactly once as the validation data. This method is particularly useful because it maximizes both the training and testing data, ensuring that every data point is used for both training and validation. The performance of neural networks is not captured by a single metric. Several metrics are used in tandem to evaluate various aspects of a model. Accuracy is the most intuitive metric, measuring the percentage of correctly predicted instances. However, accuracy may not always be the best metric, especially in cases where the class distribution is imbalanced. In such cases, precision recall and the F1 score are preferable metrics. Precision measures the ratio of true positives to the sum of true positives and false positives, which gives an indication of a model's positive predictive value. Recall or sensitivity measures the ratio of true positives to the sum of true positives and false negatives, representing the ability of the model to identify all relevant instances. The F1 score balances precision and recall and is particularly useful when seeking a balance between false positives and false negatives. Receiver operating characteristic (ROC) curves are another tool for evaluating the performance of classification models. An ROC curve is a graphical plot that illustrates the diagnostic ability of a binary classifier system, as its discrimination threshold is varied. The curve is created by plotting the true positive rate, TPR, against the false positive rate, FPR, at various threshold settings. The area under the ROC curve, AUC, provides a single scalar value to compare the performance of different models. A model with perfect prediction ability will have an AUC of 1, whereas a model with no discrimination ability will have an AUC of 0.5. Beyond singular metrics, confusion matrices are extremely useful as they visualize the performance of an algorithm. A confusion matrix displays the number of true positives, true negatives, and false negatives in a grid format. This allows not just for quantification of performance, but also helps in understanding how a model is misclassifying instances. Analysts can use this understanding to further refine their models by adjusting hyperparameters or even rethinking the model architecture in cases where systematic errors are observed. Hyperparameter tuning is an important aspect that directly affects the performance evaluation of neural networks. A neural network's architecture and learning process depend on various hyperparameters, which can include the learning rate, number of hidden layers, number of neurons per layer, activation functions, and many others. Hyperparameter tuning involves running a series of experiments to find the optimal combination that maximizes model performance. Strategies for hyperparameter tuning include grid search, where a predefined range of potential values for each hyperparameter is tested exhaustively, random search, which samples parameter values from a statistical distribution, and Bayesian optimization, which builds a probabilistic model of the function mapping from hyperparameter values to the objective evaluated on a validation set. It's important to ensure that while tuning hyperparameters, the evaluations are done on a separate validation set and not on the test set. The validation set serves to provide an unbiased evaluation of a model fit on the training dataset while tuning the hyperparameters. If the test set is used in this tuning process, it will leak information about the test data into the model, thereby violating the assumption that the test data is unseen and could lead to an overfit model with overly optimistic performance estimates. Once a model has been trained and validated, another form of evaluation is to carry out an error analysis. This involves looking at the predictions where the model was incorrect and trying to understand the reasons behind these errors. This task can often uncover insights into data quality issues, such as mislabeled data, or it can reveal patterns that the neural network is not capturing, suggesting areas for further feature engineering or modifications to model architecture. Ensuring a model's robustness is also about evaluating how it performs under different conditions. Various forms of stress testing may be employed, including introducing noise into the input data, evaluating on data that has been systematically modified, or evaluating the model's performance across different groups within the data, a process known as fairness evaluation. This rigorous testing can help in identifying weaknesses in the model and providing a more holistic understanding of the neural network's capabilities. Lastly, deploying the model in a real-world environment, an activity sometimes known as shadow testing, where the model's outputs are compared against actual outcomes without the model's decisions being acted upon, can be very instructive. This practice can reveal issues that weren't encountered during the validation phase and is the final litmus test of a model's utility before it's fully integrated into a decision-making process. Throughout the life cycle of a neural network, model evaluation and validation techniques are paramount to constructing a reliable model. These techniques work in tandem to scrutinize a model's performance, generalize its capability to new data, and enhance its accuracy in making predictions. As the intricacies of neural networks become increasingly understood, the practices surrounding model evaluation and validation will continue to evolve, fostering neural networks that are not only powerful in their predictive capacity, but also robust and reliable in practice. 9.5 Best Practices for Neural Network Development. Neural network development is a structured approach to creating effective learning models that can discern patterns, make decisions, and predict outcomes. When embarking on a neural network project, the initial steps should be the selection of relevant data. Data serves as the foundation upon which neural networks learn and extract insights. Therefore, it is crucial to choose data that is representative of the problem at hand, is of high quality, and is sufficiently diverse to train the network effectively. Failing to vet data adequately can result in networks that perform poorly on new, unseen information. Additionally, data pre-processing, such as normalization or standardization, helps in mitigating issues related to disparate data scales and improves the convergence speed during the learning phase. Once suitable data is acquired, one must decide on the neural network's architecture. This decision involves selecting the type of neural network, such as a feed-forward, convolutional, or recurrent neural network, depending on the task. Furthermore, within the chosen type, the number of layers and neurons per layer needs to be determined. As there is no one-size-fits-all, this usually requires experimentation and adjustments. It is beneficial to start with simpler models and gradually increase complexity as needed. This practice, known as model complexity tuning, helps avoid overfitting where the model learns the training data too well, including its noise, and fails to generalize to new data. Another crucial aspect of neural network development is the splitting of datasets. Best practices suggest the use of separate datasets for training, validation, and testing. This partitioning allows the neural network to learn from one set of data, tune hyperparameters on another, and finally, be evaluated on a third, unseen set. By keeping the test set separate and only using it once, one can better gauge the network's performance and its generalizability to unseen data. The common split ratio is 70% for training, 15% for validation, and 15% for testing, although this can vary based on the dataset size and the problem complexity. Hyperparameter tuning is a meticulous process involving the adjustment of learning rate, number of epochs, batch size, and other settings that are not learned through training, but are pivotal for model learning behavior. This fine-tuning is a delicate balance, as overly aggressive parameters can cause the network to not converge, while overly conservative parameters can lead to slow training without significant performance gains. Utilizing grid search, random search, or advanced methods like Bayesian optimization can aid in finding the optimal hyperparameters efficiently. Large-scale searches can be computationally expensive. Thus, it's beneficial to conduct preliminary experiments to narrow down the hyperparameter space. Weight initialization and activation functions are minor yet impactful choices in neural network development. Weights should be initialized neither too high nor too low to prevent vanishing or exploding gradients, where the weights and gradients become too small or too large to enable effective learning. Activation functions like ReLU, rectified linear unit, and its variants are commonly used for avoiding these issues and helping in nonlinear transformations. The activation function's choice directly impacts the neural network's ability to learn complex patterns, and using newer sophisticated functions like leaky ReLU or parametric ReLU can aid in particular situations where standard ReLU might not be as effective. Regularization techniques such as L1 and L2 regularization, dropout, and early stopping are instrumental in preventing overfitting. Regularization methods impose constraints on network weights or activities to promote model simplicity and robustness. For instance, dropout selectively ignores a subset of neurons during training, forcing the network to learn more redundant representations and, consequently, boosting its ability to generalize. Early stopping halts the training once the network performance stops improving on a validation set, which serves to prevent overfitting and excessive training times. Training a neural network is a computationally intensive task, and adequate computational resources are essential. Utilizing hardware accelerators like GPUs, graphics processing units, and TPUs, tensor processing units, can dramatically speed up training times. Tools and frameworks such as TensorFlow and PyTorch offer the infrastructure for seamless utilization of these resources, alongside a plethora of built-in functions for neural network development and training. Efficient computation also involves optimizing the training process through vectorization and using mini-batch gradient descent over single-sample training, which balances the benefits of batch and stochastic gradient descent. The interpretability of neural networks should not be overlooked. While neural networks are often seen as black boxes, understanding the model's decisions is vital for gaining user trust and for regulatory reasons in certain domains. Techniques like feature importance analysis, visualization of network activations, and model distillation can shed light on how networks infer their results. Interpretability serves not only to explain model predictions, but also to gain insights that can inform further improvements in the architecture and training process. Monitoring model performance in a production environment ensures the neural network continues to perform optimally when deployed. This involves setting up a feedback loop where the model's predictions are periodically assessed, and if performance degrades, the model can be retrained with new data. This process of continuous improvement helps in adapting to changing data distributions, a phenomenon known as concept drift. Finally, documentation throughout the development process facilitates better understanding and maintenance of neural networks. This includes recording data source information, transformations applied, architecture decisions, hyperparameter tuning experiments, and model evaluation metrics. Well-documented neural network projects can be more easily reviewed, updated, and shared with others, promoting reproducibility and collaboration in the development community. In developing neural networks, adhering to these best practices can lead to the creation of robust, effective, and reliable models that can solve complex problems and deliver valuable insights. While the process is iterative and may require adjustments and refinements, the structured approach outlined helps in navigating the development journey and achieving a successful outcome. 9.6 User Interface Considerations for AI Systems. When integrating a neural network into a system with user interaction, it's essential to prioritize the interface design to enhance user engagement and ensure the efficient use of the AI features. A properly designed user interface (UI) acts as a bridge between the user and the powerful capabilities of a neural network, making its complexities accessible and its outputs understandable. By considering the user's experience first, designers and developers not only create an environment where users can achieve their goals with the neural network, but also help them trust the AI's decision-making processes. User interfaces for AI systems should be intuitive, guiding users through complex tasks without overwhelming them. To achieve this, the UI should present information in a hierarchical manner that corresponds to the user tasks, often through progressive disclosure techniques, where additional options and information become available as needed. This approach can reduce cognitive load and prevent users from feeling lost within the application. Furthermore, it is wise to avoid using too much technical jargon or detailed displays of the AI's inner workings unless it serves a concrete purpose for the user's tasks. The feedback that neural networks provide to users must be both timely and relevant. Latency between user actions and the neural network's response can disrupt the user's workflow and lead to frustration. Consistent prompt feedback can keep the user informed of the AI's processes, helping to maintain transparency and setting proper expectations about the network's capabilities and limitations. For instance, when a user submits data for analysis, indicating that the neural network is processing, and providing an estimated time for completion can be beneficial. Displaying the results of a neural network's processing in an understandable and actionable format is just as important as the system's input methods. Visualization tools such as graphs or heat maps can often convey complex data more effectively than raw numbers. Users should be able to easily interpret the outcomes of the neural network to make informed decisions, whether in predictive analytics, pattern recognition, or other applications. Moreover, offering the capability to adjust the level of detail in the presented information enables users to control how much they want to delve into the results. Error handling is another critical factor in the development of user interfaces for neural network applications. Users need clear messages when something goes wrong or when the neural network can't process a request. These messages should not only state that an error occurred, but also provide guidance on how to resolve it, or at least the steps to take next. This sort of responsiveness can decrease user frustration and improve overall system trustworthiness. User control and freedom within the interface are critical for maintaining users' comfort and trust in the system. Users should be able to easily navigate through the interface, entering and exiting functions without difficulty. One strategy is to implement undo and redo functions, allowing users to explore different scenarios confidently, knowing they can revert to a previous state if needed. Such features encourage experimentation and can lead to a more in-depth understanding of the neural network's functionality. Customization can significantly enhance the user experience in AI-driven systems. By allowing users to tailor the interface to their needs and preferences, the system can become more efficient and enjoyable to use. However, customization options should be presented in a controlled manner to prevent the user from making changes that could confuse or lead to improper use of the neural network. A well-designed system might include customization features that adapt to the user's behavior over time, providing a more personalized experience without requiring active changes from the user. Security and privacy are paramount when user interface design involves AI systems, especially if neural networks handle sensitive information. The interface should clearly indicate what data the AI is accessing, how it is being used, and whether it is stored or transmitted. Transparent consent dialogues in privacy settings give users control over their data and can mitigate concerns about AI systems potentially compromising their privacy. Training and support cannot be overlooked in AI system interfaces. Especially for complex or novel AI features, users may need help understanding how to best interact with and benefit from the neural network. Offering tutorials, tooltips, and access to customer support within the UI can aid in education and troubleshooting, leading to a more self-reliant and satisfied user base. Accessibility is a fundamental consideration, ensuring that the interface is usable by as broad a user group as possible, including those with disabilities. The design should accommodate users with diverse needs by adhering to accessibility standards, such as providing alt text for images and ensuring that controls are navigable by keyboard. Voice recognition and other adaptive technologies might also be integrated to make the system usable by persons with limited mobility or visual impairments. Creating a user interface for a neural network-based AI system is a multifaceted challenge that requires attention to usability, functionality, and the human element. Developers must engage with the user's experience, building interfaces that make powerful neural network applications accessible, understandable, and reliable. By focusing on the points outlined, intuitive design, meaningful feedback, understandable outputs, error handling, user control and freedom, customization, security and privacy, training and support, and accessibility, developers can create AI systems that users can confidently and effectively navigate, harnessing the full potential of neural network technologies. 9.7 Security aspects in neural network implementation. The implementation of neural networks in practical applications carries a set of security considerations that are paramount to the integrity of the systems they serve. The security of neural networks pertains not only to the protection of the data used and generated by the networks, but also to the robustness and resistance of the networks themselves against malicious attacks and inadvertent failures. As neural networks are increasingly deployed in critical domains such as finance, healthcare, and autonomous systems, understanding and reinforcing their security is essential for preventing potentially catastrophic consequences. One of the fundamental security issues in neural networks is the protection of data. Neural networks require vast amounts of data for training, which often includes sensitive or personal information. Ensuring the privacy and confidentiality of this data is a legal and ethical obligation. Techniques such as secure multi-party computation, homomorphic encryption, and differential privacy have emerged as methods to allow neural networks to learn from data without exposing it to unnecessary risks. However, these techniques can introduce computational overhead and may impact the performance of the network. Another aspect of neural network security is the threat posed by adversarial attacks. Attackers can create specially crafted inputs that are indistinguishable from regular data to humans, but cause the neural network to make errors. These adversarial examples pose a significant risk, particularly in systems where security is paramount. Addressing this challenge requires the development of networks that are robust against such inputs, often by incorporating adversarial training or applying defensive distillation methods. Nonetheless, designing systems that can withstand evolving adversarial tactics remains an ongoing area of research. The issue of model integrity also plays a critical role in neural network security. It is important to verify that the network executes as intended and has not been tampered with. For instance, an attacker might alter a neural network to produce favorable outcomes, a practice known as model poisoning. Defending against such attacks involves rigorous testing and validation of the network's behavior under various conditions, coupled with secure deployment mechanisms that ensure the model remains unaltered throughout its lifecycle. Data and model governance policies are also essential to the operational security of neural networks. Organizations must establish clear protocols for data access, model updates, and auditing of network operations. This includes tracking who has access to the neural network's components, what changes are made, and when these changes occur. By doing so, organizations can trace any security breaches or operational inconsistencies back to their sources, enabling more effective responses to such incidents. The scalability of security measures is another factor to be considered when implementing neural networks. As systems grow and the number of parameters in neural networks increases, ensuring that security protocols keep pace with these changes becomes more challenging. Security solutions must be able to handle the increased complexity without causing significant degradation in system performance or becoming too costly to maintain. In addition to these concerns, the deployment environment for neural networks can have implications for security. Networks deployed on cloud platforms, for example, require robust network security measures to protect data in transit and at rest. The platforms themselves must be secure against unauthorized access and vulnerabilities that could compromise the neural network. For edge computing scenarios, where neural networks are deployed closer to the data source, security must account for the increased attack surface and potential physical security risks. Certification and compliance with industry standards and regulations contribute significantly towards securing neural network implementations. These standards provide frameworks and best practices for ensuring the confidentiality, integrity, and availability of data and systems. Adhering to standards such as ISO/IEC 27001 for information security management or compliance with the General Data Protection Regulation (GDPR) for data protection can help organizations mitigate risks related to neural network deployments. The interplay between neural network security and ethical considerations cannot be ignored. The decisions made by neural networks, especially in areas like predictive policing or credit scoring, can have profound impacts on individuals and society. Ensuring that neural networks are not only secure but also fair and unbiased is a complex task that involves careful design, consistent evaluation, and a commitment to ethical principles. This includes tackling issues of data bias, transparency in decision-making, and accountability for outcomes. Finally, the human factor plays a decisive role in neural network security. Education and awareness about the safe and responsible use of neural networks are crucial for all stakeholders, including developers, operators, and end users. Building a culture of security within organizations helps to foster practices that reduce the likelihood of human error, such as negligent handling of data or inadvertent introduction of security vulnerabilities during network design or deployment. Overall, securing neural networks is a multifaceted challenge that requires a comprehensive approach, blending technical solutions with governance, ethical considerations, and human factors. As neural networks become more ingrained in various aspects of daily life, the importance of fortifying them against potential security threats will only continue to grow. Organizations and individuals must remain vigilant, adapt to new risks, and commit to the ongoing process of securing these powerful tools. This commitment to security is integral, not only to the preservation of the systems in question, but also to the trust that society places in the technology that is shaping the future. 9.8 Neural networks for mobile applications. The application of neural networks in mobile technology has significantly transformed how we interact with our devices, making them smarter and more responsive. Incorporating this advanced form of artificial intelligence into mobile applications presents unique challenges and opportunities, which we will explore in this section. A primary challenge in deploying neural networks on mobile devices is the constraint of computational resources. Unlike powerful desktop machines, mobile devices have limited processing power, memory, and battery life. Therefore, neural network models used in mobile applications often need to be optimized for efficiency. Techniques such as model pruning, where less important connections are removed, and quantization, which reduces the precision of the neural network's parameters, are commonly employed. These techniques not only help in making models smaller, but also in speeding up computation, enabling real-time applications on mobile devices. Another critical consideration in mobile neural network deployment is the use of specialized hardware. Many modern mobile devices are equipped with hardware accelerators like GPUs, graphics processing units, or NPUs, neural processing units, designed specifically for fast and efficient machine learning inference. Leveraging these specialized processors is essential for running complex neural network models. Thus, developers are increasingly using machine learning frameworks adapted for mobile, such as TensorFlow Lite and CoreML, which are optimized to take advantage of this specialized hardware. Despite the challenges, the integration of neural networks into mobile applications offers considerable benefits. One significant advantage is the enhancement of user experience through features such as image and speech recognition, personalized recommendations, and natural language processing. These functionalities are becoming increasingly commonplace in mobile applications, from photo editing software that can automatically enhance images to virtual assistants capable of understanding spoken commands and responding intelligently. Moreover, the use of neural networks enables mobile devices to learn from user interactions, improving their performance over time. This learning can be done locally on the device, a concept known as on-device learning, providing benefits such as privacy preservation since data does not need to be sent to a remote server. Additionally, on-device learning can minimize latency and decrease the dependency on network connectivity, which is crucial for a seamless user experience. As an example, predictive text input and autocorrect functionalities have evolved with the assistance of neural networks. These systems can now understand the context and the user's typing habits to enhance their suggestions and corrections. This continual learning process ensures that the more a user engages with the keyboard, the smarter and more accurate it becomes, adapting to individual language use patterns and preferences. Another area where neural networks have made a substantial impact is in mobile gaming. Game developers are using neural networks to create more realistic and engaging experiences. Non-player characters, NPCs, can exhibit behaviors that are more complex and human-like, and procedural content generation can become more sophisticated, leading to more varied and dynamic game environments. By processing data quickly on the mobile device itself, these neural network-driven features provide players with a rich and immersive gaming experience, even without a constant internet connection. Besides enhancing existing functionalities, mobile neural networks are paving the way for entirely new categories of applications. Health and fitness apps, for example, use neural networks to monitor and analyze physical activity and vital signs, providing users with personalized insights and feedback. This real-time processing and analysis allow for immediate user feedback, which can be essential for applications targeting fitness coaching, medical monitoring, or even mental health. Finally, privacy and security considerations in mobile applications are increasingly being addressed through the application of neural networks. For instance, secure user authentication using biometrics, such as facial recognition or fingerprint scanning, relies on neural network-driven algorithms. These features take advantage of the model's ability to recognize complex patterns to provide a robust layer of security, which is simple for the user to use and yet extremely difficult for intruders to bypass. To implement neural networks effectively in mobile applications, developers must have a deep understanding of both the algorithms and the platform-specific constraints. Efficient model design, coupled with a keen awareness of the user experience, is imperative. Developers must continuously test and iterate their models, making sure they perform well under the varying conditions presented by different mobile devices and usage patterns. In the broader context, the robust development of neural networks for mobile applications illustrates the remarkable potential of machine learning. By surmounting the hurdles inherent in mobile computing, developers are crafting experiences that are more intuitive, helpful, and secure for end users. While the technology continues to advance, the focus remains on enhancing the ability of mobile devices to serve as intelligent companions in our daily lives, harnessing the power of neural networks to deliver sophisticated and user-centric services and features. This impressive stride in technological advancement underscores the significant strides being made in neural networks and sets the stage for more innovative breakthroughs in mobile computing. 9.9 Scaling neural networks for large-scale applications. In implementing neural networks for large-scale applications, one must consider both the size of the network and the computational complexity. As the demand for processing large datasets with high-dimensional features increases, the need to scale neural networks correspondingly becomes crucial. Scaling neural networks involves expanding their capacity to handle more data or more complex patterns without a significant increase in training time or resource consumption. This can be done by either increasing the width of a network, that is, the number of neurons in each layer, or increasing the depth of the network by adding more layers. Both of these methods have different impacts on the learning capabilities and generalization of neural networks. Increasing the width of a neural network allows the model to process a larger variety of features in parallel, which can be particularly beneficial when dealing with high-dimensional data. Wider networks tend to have a richer representation capability, as they can create more complex functions due to the increased number of neurons. However, training wider networks demands more computational power and memory. Overfitting, where a model learns the training data too well and performs poorly on new data, can also become a risk with excessively wide networks, especially if there is not enough training data to support the breadth of the model's capacity. Deepening a neural network, that is, adding more layers, can improve its ability to learn hierarchical representations of data, which is a key advantage in tasks such as image and speech recognition. As the data passes through successive layers, more abstract features can be extracted and leveraged for prediction tasks. However, very deep networks can be challenging to train due to issues such as vanishing or exploding gradients, where the gradients become too small or too large to propagate useful error signals through the network layers during backpropagation. Techniques such as residual connections, batch normalization, and improved initialization methods have helped mitigate these issues, making it feasible to train deeper networks effectively. Another aspect to consider when scaling neural networks is the distributed training of models. Large-scale applications often cannot be processed on a single machine due to memory limitations, processing power, or both. Distributed training involves splitting the data across multiple machines, or nodes, and parallelizing the computations to speed up the training process. There are two main paradigms for distributed training: data parallelism, where the same model is trained on different subsets of the data simultaneously, and model parallelism, where different parts of the same model are trained on different nodes. Each strategy has its use cases, advantages, and challenges. Data parallelism is the most common approach to scaling out training for large datasets. It works by replicating the neural network across several nodes, with each node receiving a different subset of the data. During each training step, nodes compute gradients independently, then synchronize them across the network, typically employing some form of gradient averaging to update the model parameters. This approach requires efficient communication between nodes to share the gradients and update the weights uniformly. High bandwidth and low latency networks are desirable for data parallel training to minimize synchronization overhead. Model parallelism, however, partitions the neural network itself across different nodes, which may be necessary for very large models that do not fit into the memory of a single computing device. This approach can lead to reduced communication overhead, as each node only needs to share its portion of the gradients or weights. However, it requires careful partitioning of the model to balance the computational load across nodes and to minimize the dependencies between them. Model parallelism is less common due to its complexity and the difficulty in achieving efficient load balancing. Many modern large-scale neural network applications leverage a hybrid approach combining both data and model parallelism to overcome their individual limitations. This hybrid approach may involve splitting a model into several segments, each replicated across multiple nodes so that each segment's parameters can be updated in parallel. The hybrid approach aims to achieve scalability while maintaining manageable levels of communication overhead, but it introduces additional complexity in orchestrating the training process across multiple dimensions of parallelism. Furthermore, effective optimization algorithms play a critical role in scaling neural networks. Stochastic gradient descent (SGD) and its variants, such as ATOM and RMS-BROP, are commonly used to train neural networks. However, when these algorithms are applied to large-scale problems, they face challenges like maintaining a stable convergence rate and adjusting learning rates appropriately across the distributed system. Techniques such as learning rate warm-up, where the learning rate is gradually increased to mitigate the risk of divergent behavior at the start of training, and adaptive learning rate schedules are crucial for the stable convergence of large-scale neural network training. Another important consideration in scaling neural networks is the use of efficient hardware accelerators, such as graphics processing units, GPUs, and tensor processing units, TPUs. These specialized processing units can perform the parallel matrix and vector operations, which are at the heart of neural network computation, much more efficiently than general-purpose CPUs. Using these accelerators allows for significantly faster training and inference times, and has been one of the key enablers of the recent successes in deep learning. However, the hardware itself must be efficiently utilized, often requiring a careful balance between computational operations and memory bandwidth to prevent bottlenecks. Lastly, implementing effective regularization techniques helps in scaling neural networks by preventing overfitting, which can be particularly problematic in large networks with millions of parameters. Dropout, early stopping, weight decay, and data augmentation are common regularization methods that help in generalizing the models to new data by reducing overfitting. Regularization becomes even more crucial as the capacity of the neural network increases, because the potential for the network to memorize the training data rather than learning the underlying patterns grows. Therefore, scaling neural networks require not only improvements in architectural design and computational strategies, but also a focus on maintaining the model's ability to generalize to unseen data. In summary, scaling neural networks for large-scale applications is a multifaceted challenge that necessitates a comprehensive approach, taking into account network architecture, training paradigms, optimization techniques, computational resources, and regularization strategies. As neural networks continue to grow in size and complexity, innovative solutions for efficient and effective scaling will continue to emerge, driven by the collaborative efforts of researchers and practitioners in machine learning and related disciplines. 9.10 Legal and regulatory considerations for AI deployment. As the deployment of artificial intelligence, AI systems, and neural networks becomes more widespread, legal and regulatory considerations come to the forefront of organizational operations. This section examines the various aspects of law and regulation that entities must navigate when integrating AI into their practices. An understanding of these considerations is crucial to ensure compliance, maintain ethical standards, and foster public trust. Firstly, data protection and privacy are key legal domains pertinent to the functioning of neural networks. With the essentiality of large datasets for the training of AI models, the handling of personal and sensitive information is subject to stringent data protection laws, such as the General Data Protection Regulation (GDPR) in Europe. Entities must ensure that their AI systems comply with these regulations, which may entail obtaining explicit consent from individuals for the use of their data, ensuring data minimization, and facilitating the rights of individuals to access, rectify, or delete their data. Intellectual property, IP rights, also present a complex issue in AI deployment. As neural networks generate outputs that could be commercially valuable or innovative, questions arise about who holds the copyright or patent to these outputs. The fluctuating nature of AI-generated content challenges traditional IP law frameworks, which are often predicated on human authorship and inventorship. Legal professionals, AI developers, and policymakers are engaged in ongoing discussions to clarify IP rights in the context of AI outputs, adaptations, and improvements. Liability is another major concern. When AI systems make decisions or take actions resulting in damages or injury, determining who is at fault can be challenging. Current legal frameworks are primarily tailored to situations with human actors, leaving a gray area when neural networks are involved. The legal community is debating various models, such as extending product liability to cover AI or developing a new set of AI-specific liability laws. The fundamental question revolves around attributing responsibility when harm is caused by autonomous or semi-autonomous systems. The deployment of AI technologies requires careful consideration of non-discrimination and fairness. AI systems can inadvertently perpetuate or amplify biases present in their training data, leading to discriminatory outcomes. Legislation like the U.S. Equal Credit Opportunity Act, ECOA, prohibits discriminatory practices in lending, which extends to automated decision-making systems. Companies using AI must implement fairness audits and bias mitigation strategies to comply with these non-discrimination laws and to ensure ethical standards are maintained. Consistent with the concerns regarding fairness is the requirement for transparency and explainability in AI systems. Regulators and civil society organizations advocate for the so-called right to explanation, entitling individuals to understand the rationale behind decisions made by AI affecting them, particularly in critical areas like healthcare, finance, and law enforcement. This necessitates the development of interpretable models or the provision of supplementary information that illuminates the decision-making processes of complex neural networks. The influence of AI and neural networks on competition and antitrust is growing as companies increasingly leverage these technologies to gain advantages in the marketplace. Regulatory bodies are monitoring the use of AI in business practices that could be anti-competitive, such as algorithmic price fixing or market segmentation. There is a push to update antitrust laws and enforcement strategies to better address the unique challenges posed by AI-driven market behaviors and the concentration of power among large tech companies with access to extensive data and advanced AI. Consumer protection is another realm impacted by AI deployment. Underlying this is the obligation to ensure that AI products and services are safe and reliable. Poorly designed or implemented neural networks can make errors with serious implications, like misdiagnosing patients or causing accidents in autonomous vehicles. To prevent such occurrences, rigorous testing, validation, and ongoing monitoring are fundamental, requiring adherence to consumer protection standards and potentially prompting the introduction of new regulations governing AI reliability and safety. To manage the aforementioned legal and regulatory considerations, industries and organizations must engage in ethics-based governance models. Corporate governance structures should integrate AI governance frameworks that address ethical considerations and align with legal standards. This involves establishing committees or boards responsible for AI ethics, creating clear policies for AI use, and promoting an organizational culture that prioritizes legal compliance and ethical AI use. International and cross-border considerations compound the complexity of AI deployment, given that AI systems often function on a global scale. Multinational companies must navigate a patchwork of international regulations and reconcile differences in legal standards between jurisdictions. Efforts to harmonize international regulatory frameworks are underway, aiming to facilitate the global operation of AI systems while respecting varied legal traditions and policies. Finally, ongoing legal and regulatory developments necessitate continuous engagement with the AI landscape by practitioners and organizations. Legislatures and regulatory bodies worldwide are in the process of crafting new laws, guidelines, and standards specific to AI, often with significant input from AI experts, ethicists, and the public. Staying informed about these developments is essential for organizations to remain proactive and adapt their practices accordingly. Continuous engagement and learning are prerequisites for the legally sound deployment of neural networks and the broader umbrella of AI technologies. These considerations underscore the multifaceted legal landscape that organizations deploying AI must navigate. While the technology promises great benefits, there are substantial risks and responsibilities that accompany its use. Organizations must remain vigilant, adaptive, and committed to ethical practices to successfully integrate AI within the bounds of evolving legal and regulatory frameworks.